Hey, welcome back to Mr. P Helps with Precal. This is Unit 4, Topic 1, Lesson number 1. We're going to start off with our basics of vectors in this topic. So it says here that find x and y using trigonometric ratios. So that, in this case, that would be sine of 30 is equal to opposite, which is y, over the hypotenuse, which is 9. So if I was going to solve this equation, I know sine of 30 is 1/2, and I would multiply both sides by 9, and that's going to tell me that 1/2 times 9 means that 1y is 4.5. Now, normally I'll put that into the calculator, but this is one that I have memorized. If I'm going to do cosine of 30 equals adjacent, which would be x over 9, multiply both sides by 9, 9 times cosine of 30 is about 7.79. Now, there is another way of doing this, which is just kind of bypasses all the steps I just did, because basically all I did was I multiplied 9, which is the hypotenuse, right here, and I multiplied the hypotenuse times, to find the x-coordinate, I multiplied it by cosine of the angle. And for y, I took the hypotenuse and I multiplied it by sine of the angle. And that's going to come handy later on when we're trying to find vector notation. I was trying to find the vectors in based upon what was given. You'll see. So vectors in this plane. So vectors is a way of describing the magnitude, which is the size and the direction of a force or velocity or acceleration. These are all things that could be represented by vectors because they have, so force is, there's a direction the force is going, plus there is how much of that force is going in that direction. Same thing with velocity, which is your speed in which you're going and which direction you're going, and same with your acceleration. So we have a magnitude and we have a direction that it's going. So magnitude just means the size of it, whereas direction means obviously which direction that it's going. So this is called component form, which I started on a second ago. Standard representation of vectors is a comma b using this notation with the little arrows on both sides. So this is also called, this is standard form because this happens to be at the origin on a coordinate graph, but even if it's not on the origin, then this is just technically just component form. It doesn't have to be at the starting point unless that would be your standard form of it. It's kind of like when you're graphing equations and it's like your parent function. All right, so to discuss the properties of vectors, let's first plot some points. Let's talk about the different types of vectors that you could possibly have. So 0, 0 would be this point, and B25 would be this point, and I would connect them with an arrow like such. Negative 3, 1, so that's vector AB. And negative 3, 1 is here, negative 1, 6 is here. Now what you should notice about these two vectors is that basically they're exact same length and they are going in the exact same direction. That's what I can say about both of these vectors. Now, if it's a 0 vector, that basically just means that it's just a point. It's not going in any direction, nor does it have any magnitude because it's not going anywhere. It's simply just a point. If you have parallel vectors, which is the case that you have up here, that means you have two vectors that are going in the same or opposite direction. Actually, this is equivalent, I said up here, because the only difference between parallel and equivalent is the fact that these are both going in the same direction, but they are also the same magnitude. Whereas parallel vectors might be parallel to each other, they might not be going in the same direction, or they might not be the same length. So one might be like this, or it might be like this. So they just have to be going in the same direction, but not necessarily the same magnitude. And then opposite vectors would be ones that are going in same magnitude, but going in opposite directions. So something like this. So exactly the same, but opposite directions, yeah. Okay, so write each vector in component form with these points. So 3, 2 is right here, and 4, negative 1 is right here. So component form means where it should be in standard position, so x, y. So if I took this and I moved it to standard position, that's basically what it would be. Now, in this case, Q to R, if I'm going to go from here to here, I'm going to go right 1, and I'm going to go down 1, 2, 3. And that's really it, because if I was putting this exact thing right here, it would be just like that. It would be going from Q to R. But if I go from R to Q, I'm going backwards. So now I'm going to be going -1 and up 3. So notice that these two are kind of like opposites of each other. If I went this direction, and then it's going to be kind of the opposite, which looks right there. We can find a complement. If an arrow has an initial point, x1, x and y1, and a terminal point of x2 and y2 is represented by this vector. So you will notice that this is basically the exact same as the slope formula. So x sub 2 minus x sub 1 and y sub 2 minus y sub 1. And that's really all you're doing, because we're finding the slope. And you'll notice I even counted the slopes, because that's really all it is in component form. It's basically just the slope. It's the direction that it's going. So prove that RS and PQ are equivalent by showing that they represent the same vector. Well, if they're equivalent, then they would have the exact same slope. So RS, which will be this minus this, and this minus this. So then we're dealing with, so RS would be equal to 2 minus -2, comma, 4 minus -1. We can clean that up a bit, and 2 minus -2 is 4, and 4 minus -1 is 5. So that's 4, 5. And then I would do the same thing for PQ. So PQ is going to be 1 minus -3, comma, 4 minus -1. 1 minus -3 is 4, and 4 minus -1 is 5. So there. We've just proven these two are exactly the same, so therefore they are equivalent vectors. They're the exact same slope. And I will do the same for the other one, but for the sake of time in this video, I'm going to move on. So magnitude, remember, is the size, and from a component form is just like using the slope formula. So, or in this case, I'm going to be finding the magnitude. So finding the magnitude is basically doing the Pythagorean theorem, because you have a right triangle. So this is really a squared plus b squared. It's the square root of a squared plus b squared, which would give you c squared. But then you do square root of both sides. So basically the magnitude is really just the hypotenuse. So if this is a and this is b, a squared plus b squared equals c squared. So this formula makes sense because the magnitude is really just the hypotenuse of a right triangle. So if I know this is 2 and I know this is 3, I can plug those numbers in and I can solve for it. Well, what if I'm given 2 different points? What if I'm told where this point? What if it's not in standard notation? Well, if it's not in standard notation because you don't have to have it at the origin, then you need some other way of doing it. And this is basically the same as the distance formula. And the distance formula is just the distance of the hypotenuse. Find the magnitude of these two. So that would be square root of -3 minus 2 squared plus 2 minus 5 squared. Okay, so calculator work is going to tell you that -3 minus 2 is -5, and 2 minus 5 is -3. -5 squared is 25, plus -3 squared is 9. That makes square root of 34 is your answer. Actually, didn't even need a calculator. I'm just going to leave it like that because that's the most precise. I don't want to round it using my calculator. All right, so finding the magnitude of each vector. So what if we're just given a point? So like we said a second ago, so this is in standard notation. The assumption is that we are using 0, 0 in standard form. So therefore, it's going to be square root of -1 squared plus 3 squared. Which happens to be 1 plus 9, which happens to be square root of 10 is the magnitude. So U is square root of 10. So this means magnitude. So the magnitude of U is square root of 10. Vector of 2, 6. So that's going to be 2 squared plus 6 squared, which equals square root of 4 plus 36, which happens to be square root of 40. So the magnitude of V, so remember the 2 lines on both sides means magnitude. So if this is vector V, the magnitude of V is square root of 40. All right, so now find the component form and the magnitude of the vector of RS. Okay, so finding the vector of RS, these are two things that we've done so far. Now, keep in mind that R is the initial point because that's the way that it's going. So it's from R to S, so that's Y sub 2 minus Y sub 1. You just got to be careful that you make sure that you're doing it in the right order, because if you don't do it in the right order, you're going to get the exact opposite of the answer. So it's going from R to S. That's the initial value. So this is Y sub 2 minus Y sub 1. So 2 minus negative 2. And then negative 8 minus 5. So we now have 2 minus negative 2 is 4, comma, negative 8 minus 5 more makes negative 13. So there's our vector, and that should be a better arrow. And it does also say also find the magnitude, so I would then do 4 squared plus negative 13 squared, which happens to be 16 plus 169, and therefore our magnitude of RS is the square root of 15, 6, 7, 8, 185. It looks like square root of 185. And once again, for the sake of saving time, I'm going to move to the next slide. I'm already at 11 minutes. Can we find the component form using an angle and direction? So we're given this angle form. Now, remember back in the warm-up, we talked about this, how this x is really just sine of the angle. Remember, sine of this angle is going to be the same as sine of 120 because so this is a 120-degree angle, which is the same as this reference angle of 60. This is a reference angle of 60. Sorry, don't know why it took me that long to think of that. So always hypotenuse times sine of 120 is going to give me this angle, and cosine is going to give me this angle. All right. Okay, so finding my vector, that's going to be the magnitude in this case, which we know is 15, times cosine of 120, comma, 15 times sine of 120. And this is where your calculator is going to do the work for you. So 15 times cosine of 120 gives me negative 7.5. Make sure, yeah, I'm in degrees. And 15 times sine of 120 is going to give me 12.99, which I'm just going to say is the same thing as 13. So there's my component form. Can we find the component form using angle and direction? So there we go. That's the component form of that question. Once again, I'm already at 12 and a half minutes, and I only have a couple minutes left, so I'm going to move on. Find the component vector in the direction of 115. Actually, I'll do one more of these, and I'll skip this one. So this would be 7 times, and this, by the way, makes sense because you're going negative 7.5, so it's going to the left, and it's going up 13. So I just want to make sure that it does make sense in the end. The fact that it's negative, comma, a positive means it's going to be in quadrant 2. So this is magnitude times cosine of 220, comma, sine of 220. Whoops. All right, 7 times cosine of 220 gives me negative 5.36, and 7 times sine of 220 is about negative 4.5. And that makes sense because that's going to be in the third quadrant. That's a negative and a negative. All right, so one more skill I want to cover in the 1 minute that I have pretty much. What do you think we can do to find an angle? So if we know that it's 3, 5, we know it's going to be in the first quadrant because this is 3 and this is 5. So the way I'm going to do this is I'm going to use inverse tangent because to find this angle, I can use tangent of 5 and 3. So tangent inverse equals y over x, that's y over x. So inverse tangent of 5 divided by 3 gives me 59 degrees. So this angle must be about 59 degrees. So negative 2, 7 would be negative 2 this way and 7 this way. So once again, I'm going to use inverse tangent. So tangent inverse of 7 over negative 2 Inverse tangent of -7 divided by 2, and that gives me -74 degrees. Now, -74 degrees plus, I got to add 180 to that, and I'm going to get 105 degrees, and about 105.9 degrees. I'm going to have to stop right there. I'm going to do more examples of these in another video, but this was, I promised, my last slide I was going to get to. Thanks again for watching. Have a great day.